Go. Hello and welcome back to Calculus 1, Part 2 on the chain rule, 3.7. Last class, we defined the chain rule as the rule where you break your function into, decompose your function into parts, and then see how many of those functions you have, and that amount of function will correspond to the amount of terms, factors that you have in your chain rule derivative. So we said we had 4 functions which would turn into 1, 2, 3, 4 derivatives, and then we simplify. So to review this, we'll start with some, let's call it a vanilla example. The derivative of e to the x squared plus x minus 3, let's say. So if you have this as your derivative, you quickly realize that the overall function is e to the x, right? So that would be your, let's use the red like last time. So f would be e to the x, and then g, which is the function plugged into this one, is x squared plus x minus 3. So now the derivative of e is itself, we keep g plugged in, times the derivative of g, which is 2x plus 1. And then we simplify it as 2x plus 1 e to the x squared plus x minus 3. So that was what we did last time. In some cases, you are going to have the derivative, the function, sorry, to have multiple functions inside, not just 2. So that would be a little bit spicier case, where you might have that sine cubed of, let's say, x squared plus 5. In this case, what would be the outer function? What do you guys think?
X cubed.
Beautiful. And then g, going one step in.
Sin.
Sin x.
Perfect. And then going all the way down to the third level, x squared plus 5. So now we need to take these derivatives. If my first is x cubed, that means 3x squared. Now, what is the inside? It is sine of x squared plus 5. Then we dig 1 in. So the derivative of sine is cosine of x squared plus 5. And finally, the derivative of the inside is 2x. So anytime you have this inner g that stays unchanged, that's the next step to take the derivative of. And then the next function within was this one, whose derivative is 2x. Now, we do not go further taking derivative of 2x because we are already done. We had 1, 2, 3, 1, 2, 3, and we are done. We are set. The problem is solved. Now you can make this look a little bit prettier, right? By putting a 6x in front and then writing your sine squared x squared plus 5 times cosine x squared plus 5. And, that little bit compresses the answer. This is in factored form. We do not want to compress this any further because now, in chapter 4, you can just, when you set this equal to 0, each one of these will be equal to 0, and you can solve each equation separately. That's chapter 4. What I'm saying is you want it to stay in the factored form. You don't want to, FOIL and do. You constantly keep factoring because factors are good for equations to solve equations. Now, what are the types of problems we did not work on last time?
Can
Those,
you take
uh-huh.
can you take the derivative of the answer, like do the chain rule on the answer?
Oh, you want the second
Like a
derivative
double?
over here?
Yeah.
Oh, my friend, you have a triple product rule. The answer is yes, but you have a triple product rule. You have to look up how to do triple product rule because the triple product rule is, like your regular product rule is F times G. Over here, you have F times G times H. So if you want to take the product rule there, you will have to do what is known as a triple product rule. There is a formula for that. There is also a way that you can, group these and solve them. But yes, you can find the second derivative in the chain rule and the third and the fourth and the 107th, right? It's just a lot of mess, to get these, because the first one is complicated enough. Now, second and a third derivative is really going to make you go crazy. Great question. Now I need to talk about a skill that you all need to have to differentiate between different rules. So I'm going to have um, a problem that says find the derivative of sine of e to the 3x plus 1 versus find the derivative of sine x times e to the 3x plus 1. I mean, you can put this one in parentheses as well, whatever. Now, if there are no parentheses that are just like this, would anyone volunteer to tell me what is the difference between these two problems?
For the first one, you would be distributing.
Okay. So this is an exponent. This 3x plus 1 is the exponent, so I can't distribute anything.
So isn't like the e to the 3x plus 1 just like inside sine versus the second one is sine x times e to the 3x plus 1?
Excellent. Yes, go ahead, say it.
I was just gonna say there's like sine x, so you have that value multiplied by e to the 3x plus 1, which
Yes.
would give you a different value than what's on the left side, because that would just be sine of e to the 3x plus 1.
Yes, and the YouTube chat has it also. That YouTube chat is the only one that said this is a product rule on the right. So this one over here, this side is the product rule. Product with chain inside, because this is e to the 3x plus 1. That's a chain rule, right? You have a linear function on top of e. It's not e to the x, right? It's a linear function of 3x plus 1. So that was really good, right? So we do have this idea of two functions are multiplied, f times g, but then this g function is actually function composition, where here you just have f of g of h. So no product rule here. This is double chain. So I'm just going to call it double chain rule, because what do you have? 1, 2, 3 functions. right? So those are the differences between problems. And what was the different? Even if I just put these, if I put these parentheses like I have over there, the difference is this x, that it's there or not there. Sin is religious term. Cos has no meaning. Tan is, right, tanning, right? You go outside on a beach and you tan, right? Those are not terms in mathematics. Sine of x or cosine of theta or tangent of alpha, you have to have something following this. These are not mathematical terms. They're completely meaningless in mathematics until you put some kind of an angle following that one. So now you can see that this sin over here has this as an angle. So it's a chain rule. Where this sign over here has x as an angle. So it's complete. It has its own angle, so it's its own function. Where this sign on the left does not have its own angle, the entire e parenthesis is its angle. We call that argument in mathematics. So when you say cosine of x squared plus 1, we call this argument. Argument of the square root. Argument of ln. So argument, that's the mathematical terminology for whatever is stuffed into sine or ln, or right. So we use that as that's the wording. So if you take a look at proper mathematical notation and carefully look at the two problems, you see that argument of this sign is entire e function. So this is going to be a double chain rule because e has its own chain rule later on. But in this case, in the second case on the right, sine x is complete function on its own, and then e is a separate function, and they have the multiplication in between, which means it's a product rule, and then yes, we'll have to do the chain rule when we get to e. So let's solve both of these problems. On the left-hand side, the outer function is the sine, and then we dig inside for e, and we dig inside for the linear 3x plus 1. Derivative of sine is cosine. Keep the guts of the sine the same. I call this over here, I should call it arguments, but I call it guts. All right. So keep the guts of that first function unchanged. Then dig one in. The derivative of e to the x is itself. Okay. Keep the guts. And then finally take the derivative of that 3x plus 1, which is 3. So I did have 3 functions. It's a double chain, right? Because this is called a chain. This is called a chain. And we have this original derivative for the outer function. So it's a three factors in this answer, but it's a double chain because sine it's not sine x, it's sine of some mess, which means a chain rule, and it's not e to the x, it's a mess up there as well. So it's another chain. It's a chain within chain. And now all I need to do is to make this look pretty, and we do that by placing 3 first. Then you put exponential function, and then you put your trig function at the end. And that would be it. On the right-hand side, we have a product rule. And the product rule formula, which we memorized from before, right? The derivative of uv is uv prime plus vu prime. This formula will be recycled in every course after Calc 1. You will have this formula a couple of times in Calc 2, a couple of times in Calculus 3, and also in differential equations to work on integrating factor method to solve equations. it will also have that formula. So it's very important. It's used a lot. And it says copy the first function as is, take derivative of the second, then copy the second, and then take derivative of the first. So here we go. The derivative is equal to copy the first function, that's sine x. Derivative of the second function, well, that's chain rule. We have e to the 3x plus 1 times the chain, the derivative of what I called the guts earlier, the derivative of that is 3. Plus, copy the second function times derivative of the first function, derivative of sine x is cosine x. We can factor out e to the 3x plus 1, and in parentheses we have 3 sine x plus cosine x. And you can see that it's a vastly different answer, right? Because one was a chain rule, the other one was product rule. So be very careful with notation. Make sure you have your arguments for sine and log and all of these functions. Make sure you have them around. We are going to work on 2 more problems. One is going to be the tangent line, and the other one is going to be second derivative by the popular demand. Find the tangent line for y equals x. Well, I'm having a feeling that I did this. Maybe I did it in the other class. At x equals to, let's go with -2. So the second one in the book. This is problem 92. Have I done this? No, we only did the vanilla examples. Okay, good. All right, so we don't care, right, which section we are in chapter 3. They all have tangent line calculations. The section will just determine the way you take the derivative. The rest of the procedure for tangent line is always the same. So we start with the derivative of the function, and once we find the derivative, we plug in the number to come up with the slope. What kind of a derivative is this?
Product with chain rule.
Excellent. So if we write this square root as 1/2 exponent, we do have a product rule as a boss, and the chain rule, right, is in the second term. So let's go. Copy the first function, take the derivative of the second function, and now you have to take the derivative of the inside as a chain rule. That's our chain rule. And then we go plus, copy the second function, which is 5 minus x squared to 1/2, times the derivative of x is 1. Now we need to clean this up a little bit. So 1/2 cancels 2. And we have -x divided by square root of 5 minus x squared. So this negative exponent pushes the square root down. And then you have plus the square root of 5 minus x squared. So that's our derivative, dy dx. Slope is the derivative computed at x equals -2 in this case. So all I need to do is to say -2 divided by the square root of 5 minus -2 squared plus square root of 5 minus -2 squared. -2 squared is +4. 5 minus 4 is 1. And square root of 1 is 1. So this whole mess becomes 2 plus 1 equals 3. The entire mess is 3. So now we have that the slope of the tangent line is 3. We need the y value because we want to find the equation of the line. I need x, y, and m. So I can calculate b. So I need y. Original function is good job, YouTube chat. YouTube chat found my mistake. Very good. Connor, you're the boss. There is an x over here, and there is an x over here. X times x is x squared. So this needs to be -x squared. Very good. So this needs to be a square over here. And when that's squared, -2 squared is 4. So this becomes -4. So that's a -4 plus 1 gives -3. So the slope is -3. Very good, very good. All right, let's go with this one now. -2 times the square root of 5 minus -2 squared. That's just -2. So my point is -2, -2. And I have the slope of 3. Y equal mx plus b for linear lines. Y is -2, slope is -3, x is -2 plus b. -2 is equal to 6 plus b. b equals -8 when you subtract 6. Tangent line, y equals -3x minus 8. There it is. Now, this is the tangent line at x equals -2. If you go to a different x location, then the slope changes, the y-intercept, everything changes, right? Because the tangent line is unique to the location of x equals -2 in this case. If you change -2, all of the calculations immediately change to find another line. Now, let's say you want to check this, right? Let's say you care. How would you check it? The fastest way is to graph these two lines. You have a function and you have the tangent line. If they touch at -2, -2, you know, right, and one is the tangent obviously to the other, then you know it's good. If they're apart and they are not touching at -2, -2, or they're touched at some other point, then your answer is completely wrong. There is no doubt about that. So make sure you type in the functions in your graphing utility. Generally, I like to use Desmos to, let's see, Desmos, graphing calculator. Oh wait, I also need to share this so that you guys can see. So here is the Desmos Share. And in one function, we type our x, neither that, there we go. X times the square root, so we'll deal with that later, 5 minus x squared. So we have a square over here. There we go. Escape that, close the parenthesis, and then raise everything to 0.5 because that's what, right, half exponent means. That, so we have this one. And then on the second one, we have our tangent line. That was -3, if I remember. X, -3x, -8. I think it was -8. Yeah, -8. -3x, -8. Moment of truth. So we see that the red and blue line, right, they are tangential at -2, -2. So we know this is all good, right? You have your red function, which is the original function. You have your blue line, which is the tangent line, and they touch, they say they kiss, right, at -2, -2. Good. So that's the way to check your tangent lines. So one more problem, and that's it. So let's go back with the share to our notes over here, and let's take a look at one more. Let's go with problem 87. It doesn't really matter. They want a second derivative of y for function y equals sine x squared. Well, let's take one derivative and then take the other derivative when you're done with the first one. So go ahead. I'll give you some time to try this on your own. Do we all have the first derivative same?
Yeah, that's what I got.
Awesome. Now, what do we do for the second derivative?
Would it be negative 4x squared sin x plus 2 cos x squared?
I don't know what the answer is. I was just looking for the concept.
Oh,
It
sorry.
sounds good. No, it sounds correct. I'm very happy that you probably have it. I'm just wondering which concept should I use?
Product rule.
Yes. Very good. Product rule. Function number 1, function number 2, they are multiplied. Therefore, copy the first. The derivative of the second is going to be negative sine x squared times 2x. This is a chain rule because, right, there was a chain rule there. Plus, copy the second times derivative of the first, which is just 2. And now, I mean, there is no point in factoring 2 in this case, because it really doesn't contribute very much. But I am going to write 2 cosine x squared first, and then minus 2x. Oh, that's not, it's a 4x squared. There we go. Because this 2x times this 2x is 4x squared. Sine of x squared. There we go. That's it. That's the second derivative. So a little bit more mess than usual. Any questions, concerns about chain rule? And if not, we are going to take a short break. And then we will deal with 3.8 implicit differentiation, which is dealing with chain rule again. It's just a little bit different angle on it. All right, so see you soon.